Hey everyone, welcome back to the channel. I'm Sandeep Kumar, and I'm so excited to be your guide on this electrifying journey through 10th grade electricity. We're going to break down this fundamental force of nature piece by piece until you're not just confident, but actually excited about solving electricity problems. It's the reason your lights turn on, your phone charges, and your heart beats. Let's get started. Let's begin our journey with the most fundamental concept: electric charge. Imagine tiny particles much smaller than atoms carrying a property we call charge. Some have a positive charge like the proton, and some have a negative charge like the electron. Now, just like magnets, opposite charges attract each other, and like charges repel. This simple rule governs how electricity behaves. When we talk about static electricity, like when you rub a balloon on your hair and it makes your hair stand up, it's all about these charges interacting. We measure electric charge in a unit called Coulomb, named after the French physicist Charles-Augustin de Coulomb. One lightning bolt can carry about 15 coulombs of charge. That's a lot of electrons moving very quickly. For now, just remember that electric charge is a fundamental property of matter, and it comes in two types: positive and negative. Now that we understand electric charge, let's talk about electric current. Imagine a river flowing. Instead of water molecules moving in an electric current, it's charged particles, usually electrons, that are on the move. The flow of these charges is what we call electric current. Think of it like this. Imagine a wire is like a pipe filled with tiny marbles or electrons. When we apply a force, like from a battery, it's like tilting the pipe. The marbles start to roll, creating a flow. That's our electric current. We measure electric current in amperes, or amps for short, named after André-Marie Ampère. An ampere is a measure of how much charge flows past a point in a circuit every second. To give you an idea, a typical household light bulb might draw about 0.5 amps, while a hairdryer could use 10 amps or more. But just like a river needs a path to flow, electric current needs a closed loop, or circuit, to travel. If there's a break in the circuit, the current can't flow. We've talked about charge and its movement as electric current. But what makes those charges move in the first place? That's where potential difference, also known as voltage, comes in. Think of potential difference as the push or pressure that compels those charges to flow. Imagine a waterfall. The water flows from a higher point to a lower point due to the difference in height, right? Similarly, in an electrical circuit, potential difference is the difference in electrical potential energy between 2 points. The greater the potential difference, the stronger the push on the charges and the greater the current flow. We measure potential difference in volts, named after Alessandro Volta, the inventor of the battery. A standard AA battery, for example, has a potential difference of 1.5 volts. Without a potential difference, there's no push, no flow of charge, and no electric current. Chapter 4. Ohm's Law, the Relationship Trio. We've explored electric charge, current, and potential difference. Now let's tie them together with Ohm's Law. Named after Georg Simon Ohm, this law describes the relationship between voltage, V, current I, and resistance, R. Ohm's law states that current is directly proportional to voltage and inversely proportional to resistance. Increase voltage, and current increases if resistance stays the same. More pressure in a hose, voltage, means more water flow, current. Increase resistance and current decreases, keeping voltage constant. Pinching the hose adds resistance. The flow of water, current, decreases even though the pressure, voltage, stays the same. Mathematically, Ohm's law is V equals 1 times R. This simple equation helps us understand and calculate electrical quantities in circuits. Chapter 5. Resistance, the current controller. In the last chapter, we encountered resistance while discussing Ohm's law. Now let's dive deeper into this crucial concept. Imagine you're trying to push a heavy box across a rough floor. The floor's roughness makes it difficult to move the box. It offers resistance to the box's motion. Similarly, in an electrical circuit, resistance is the opposition to the flow of electric current. It's like the friction that the charges experience as they move through a material. Resistance is a property of the material itself. Some materials, like copper, have very low resistance, making them excellent conductors of electricity. They're like smooth, slippery surfaces for charges to flow through. Other materials, like rubber, have very high resistance, making them good insulators. They're like rough, bumpy surfaces that hinder the flow of charge. Resistors are essential components in electrical circuits. Chapter 6, Series and Parallel Circuits, two different paths. Now that we understand the basics of electric circuits, let's explore two fundamental ways to connect components: series circuits and parallel circuits. Imagine you have a string of holiday lights. If one bulb burns out, the entire string goes dark. That's because they're connected in series. The current has only one path to follow. In a series circuit, the components are connected one after another, forming a single pathway for the current to flow. The same current flows through each component, and the total resistance of the circuit is the sum of the individual resistances. Now, imagine the lights in your house. If one bulb burns out, the rest stay lit. That's because they're connected in parallel. Each bulb has its own separate path back to the source. In a parallel circuit, the components are connected across each other, creating multiple pathways for current to flow. The voltage across each component is the same, but the current through each component can be different, depending on its resistance. Chapter 7, Heating Effect of Electric Current. Feeling the heat. Have you ever noticed that a light bulb gets hot when it's on? Or felt the warmth from an electric heater? That's the heating effect of electric current in action. When electrons flow through a conductor, they collide with the atoms of the material, transferring some of their energy. This causes the atoms to vibrate more vigorously, increasing the material's internal energy and therefore its temperature. Think of it like this. Imagine a crowded room where people are trying to move around. As they bump into each other, they transfer energy, and the room gets warmer. The amount of heat generated depends on the current flowing and the resistance of the material. The higher the current or resistance, the more heat is produced. This heating effect is the principle behind many everyday appliances, like electric heaters, toasters, and hair dryers. However, the heating effect can also be undesirable in some cases. For example, in electrical wires, excessive heat can lead to energy loss and even fire hazards. Chapter 8. Electric power, the rate of energy transfer. We've talked about energy transfer in the form of heat. Now, let's broaden our understanding to electric power, the rate at which electrical energy is transferred or consumed in a circuit. Think of it like this. Imagine filling a bucket with water. The amount of water in the bucket represents energy, while the rate at which you fill the bucket represents power. Electric power is measured in watts, named after the Scottish engineer James Watt. 1 watt is equal to 1 joule of energy transferred per second. The power consumed by an electrical device depends on the voltage applied and the current flowing through it. Mathematically, power is calculated as P equals V times 1. This means that a device connected to a higher voltage source will consume more power for a given current. Chapter 9. Household electric circuits powering our homes. Let's apply our knowledge to understand the electrical circuits that power our homes. Imagine your house's wiring as roads with electricity flowing like cars carrying energy. The power grid delivers electricity to our homes through a service drop. Electricity enters through a meter, measuring our energy use. The main switch lets us disconnect the house from the grid in emergencies. Electricity flows through a circuit breaker panel with multiple breakers. Each breaker protects a specific circuit, like lights or appliances. If there's a short circuit or overload, the breaker trips, preventing damage. Chapter 10, Safety Measures. Respecting the power of electricity. We've explored the fascinating world of electricity and its many applications. However, it's crucial to remember that electricity can be dangerous if not handled with care and respect. Always remember that water and electricity are a dangerous combination. Never touch electrical appliances or outlets with wet hands, as water can conduct electricity and increase the risk of electric shock. Be mindful of frayed wires or damaged insulation, as these can expose live wires, increasing the risk of electric shock. Always replace damaged cords and avoid using appliances with visible wear and tear. When working with electrical appliances, always unplug them before cleaning or making any repairs. This simple habit can prevent accidental shocks and ensure your safety. Never overload electrical outlets by plugging in too many devices, especially high-power appliances. Overloading can lead to overheating, increasing the risk of fire. And there you have it, a whirlwind tour of 10th grade electricity. I hope you found this video helpful in demystifying this fundamental force of nature. Remember, understanding electricity is not just about passing exams, it's about appreciating the invisible world that powers our lives. If you enjoyed this video and want to see more content like this, don't forget to give it a thumbs up and subscribe to the channel for more electrifying lessons. Keep those brains sparking, and I'll see you in the next video.